In today's video, we're going to be debunking quantum mechanics, and quantum mechanics is a really good example of sensationalist science. I talk a lot about this in my video on science. This is where people gravitate towards really weird and interesting ideas instead of truthful ideas in order to get science more funding. Alright, so we hear all this stuff about multiverses and teleportation, and when you look at things, it causes the universe to unify, and there's multiverses and all this stuff. And this stuff isn't just coming from a bunch of people misinterpreting quantum mechanics. In Steve Patterson's video, he's investigating specifically this, and the Oxford professors are teaching the following things. First, that we live in a multiverse is probably a fact, and secondly, that nothing in reality happens until you look at it.
Up to the point where we look.
The point where we look is, as it were, the last resort. If you can't find a way to block it before when we look, then it must be the very act of looking that does it. Which is precisely why they say. So I want to make that very clear, because for me, in terms of like coming from a position of, I'm very sympathetic to common sense. The idea, tell me if this is a correct analogy. So let's say that I was flipping a coin, and 50% of the time I get heads, 50% of the time I get tails. And I can't know beforehand, because I have some inherent limitation, I can't know whether or not it's going to be heads or tails. But I have a probability function. I say 50%, 50%. It would be as if it appears. What I'm saying is, when I flip the coin is in a state of heads and tails, but when I look, boom, it pops into one state. Is that a fair analogy?
Right.
Now, that seems to me, if it's not outrageous to say, that seems absurd.
Right. Yeah. Well, I think seeming absurd isn't a great
counter-argument
method, really, in debating these things. Sure, it may well seem absurd.
But that's a fair way, that is a fair...
It's a fair characterization of what going. The flipped coin is in a superposition of being spin up and spin down, whatever the word superposition means. It's somehow maybe not interpretable in ordinary terms, but when I open my eyes and I look, boom, then I must see either the coin head or the coin tail. That must happen.
Alright, I'm going to try to prove to you without a shadow of doubt that all of this is nonsense. It's just layers and layers of nonsense hidden in a bunch of technical jargon. Okay, so this is my magical fairy here. And she has two superpowers. The first one is whenever you look at her or sense her in any way, she disappears. So there's no way to actually see her. She's always one step ahead of you. So for example, if you set up a bunch of cameras, she knows where all the cameras are and she'll avoid them all. If you stare at her, she disappears. If you hear her, she'll become silent, right? Or if she's making noise and you step into the room, she'll instantly become silent. Whatever you do, she's one step ahead of you, and there's no way to sense her. Now the second thing she can do is that if you observe any of the effects the fairy has on reality, the effects themselves also disappear. So this fairy sprinkles pixie dust all over your bedroom, and all of a sudden there's a bunch of big flowers growing, right? But as soon as you open the door and you observe, this is an eye, not the best drawing of an eye. As soon as you observe any of the effects themselves disappear. So my question is there any way you would accumulate evidence of the existence of the fairy, or know that the fairy exists through evidence? And the answer is obviously a no. I can't think of any, and I mean, take me up on this. I can't think of a single possible way that you could know of the existence of this fairy in the first place. Alright, so this is the two-slit experiment. If you guys are already familiar with this, just skip through this. I'm just going to explain how it works, and if you don't like my explanation, just look it up on YouTube. There's probably better videos with better animations than this, but anyway, so you have this gun here which shoots photons, and photons are like this particle that light is supposedly made out of, right? And it's going to be a lot easier if you kind of imagine it like this is a actual gun which shoots like bullets and stuff, right? There's a little trigger. And you have a metal plate here which will block the bullet and deflect it. But if it goes through one of these slits, then it's going to hit this wooden board in the back. And if you did that, what you'd expect is you'd get a pattern something like this. Right? You get a concentration of bullets and then a few that angle off like that. And, you know, when it goes through this slit, when you fire it and it goes through this slit, it's going to hit this wall here and make a pattern like that. And when you fire it and it goes through this slit, it's going to hit this wall and make a pattern something like that. If the gun is somewhat random. If it's a very precise gun, then it would hit the same place every time. If the gun is a little bit of imprecision, which it obviously must in order to go through these slits, because the gun is actually aimed at the center here, right? So in order to actually go through the slits, the gun has to be somewhat imprecise. And that's what you would expect. But what happens is instead of getting this pattern you'd expect, you get something really weird, which is an interference pattern from waves. And it's a bit hard to draw, but it's a whole bunch of bands like this. And in short, if you were firing like a water wave, if this gun shot like a wave of water, when it goes through the two slits, it causes this interference pattern. And it's a bit hard to draw it out, and I'm not too good at explaining that. But in short, you get this really weird pattern, which is what would happen if you were shooting a wave instead of a particle. Now, what gets weirder is when you set up a camera here, when we put up a camera here, when you set up this camera, all of a sudden, it changes from a wave pattern back to a particle pattern, and it looks like as if you were shooting bullets again. So this camera completely changes how the photon behaves. Okay, so to debunk quantum mechanics, what we really need to look at is this concept of observation and what observation means. And this is one of the fundamental things in philosophy, which is to define things clearly, which is where all the obscurity and all of the ideas of quantum mechanics are able to be sustained, because you don't have a clear definition of observation. However, the experiments give us a clear definition of what observation means. So we have our photon shooting through the gun, and when we observe it through the detector, this is what changes the behavior, right? It's all about the detector. Now, when we look at the board, when we look at all the bullet holes, or whatever you want to call them, right? This does not affect the behavior of the photon, all right? Observing the effect, and this is really important, observing the effect of the photon does not affect the photon behavior. Okay, so we are allowed to observe the effect. Looking at the bands on the wall does not change how the photon acts. That does not count as an active observation. And we know that observing the photon itself is an observation and does change its behavior. And we know this from the two-slit experiment itself, right? So we are allowed to observe the effect, but we're not allowed to observe the photon itself. And this is going to be very useful and good to debunk quantum mechanics. All right, now going back to the Steve Patterson video, what the professor is claiming is that reality exists in a superposition. There's this multiverse where the coin exists in a heads and a tails superposition, and until you actually observe it, it doesn't take on a definite form. And I'm going to say that that is clearly nonsense, and we can debunk that very easily now. So what I'm going to do is I'll take our coin here, And on the head side, we're going to cover it with this chemical reactant. We're going to put a patch of this chemical reactant on. It's a very strong explosive. And when this blue stuff mixes with this orange stuff for 5 seconds, kaboom, we get a big explosion, all right? So what we're going to do is we're going to take a whole bunch of these coins and a whole bunch of this orange stuff, and we're going to flip them. And as you can probably guess, the results are going to be exactly what we would expect. 50% of the time, we will get an explosion, and 50% we won't. And it won't be exactly 50-50, but the more we do it, the closer it'll get to 50-50 by the law of large numbers. So, according to the professor, if the coin is existing in a superposition and it hasn't taken on a heads or tails form until it's observed, then when we observe the effect of the coin, we should see both an explosion and a non-exploded state at the same time. Now, what quantum apologists are going to say is that the explosion itself, they're going to say the explosion is an act of observation. And this cannot be the case. Because first of all, as we showed previously in the double slit experiment, you're allowed to observe the effects of the photon. In this case with the explosion, we're not observing the coin itself in any way. There's no way we're observing the coin. We're only observing the effect of the coin. We're observing the effect of the coin toss, not the coin itself. And then they're going to say, well, you're not allowed to observe the effect either. Observing the effect is the same as observing the coin. And this brings us back to the fairy experiment. All right, so at the start of the video, we were talking about this fairy, and I think I convinced you that if we cannot sense the fairy in any way, and we cannot observe the effects of the fairy in any way, it would therefore be impossible to actually know of the existence of the fairy in the first place. And the exact same thing is true with quantum mechanics. If we can't look at the panel with all the bullet holes, right? We can't observe the effects of the photon, and we also cannot observe the photon itself, then we would have no knowledge of the double slit phenomenon in the first place. How would we even know of the existence of this phenomenon? Okay, so I talked to a quantum computist. I don't know if computist is a word, but he's an expert in quantum mechanics, and I think he's a very sensible guy and has a very good explanation for what's going on. And basically, you have to ask the question, what does it actually mean to observe? What does observe mean? And what it means is you bounce light, like if I have an object here, say a little ball, to observe it means to bounce light off of it and then into a sensor, like a human eyeball or some kind of computer thing that can read it, a computer sensor, right? So what these detectors do when you set up the double slit experiment is it's bombarding that photon. You shoot the photon through the gun, and the detector is bombarding it with light, and if the light bounces back into the sensor, this is how it measures whether the photon went through the slit or not. So it's the act of bombarding the photon with a crap ton of light that throws the behavior of the photon off. And that makes sense, because when you're dealing with these super small, ultra microscopic particles, if you're bombarding it with light, I would expect it to have a very large effect. If you're bombarding something, very big with a beam of light, it's probably not going to affect its behavior all that much.